Hello, Principles of Engineering. Today we're going to talk about hydraulic power, how to calculate how much hydraulics can lift, why hydraulics are better or worse than pneumatics. We'll go through a couple of example problems, and that'll be our time together. Let's get started. Number one, hydraulic power. Number one, hydraulics, it's a liquid. And liquid under pressure is not compressible. It says it's compressed very little. This is the major difference between hydraulics and pneumatics. Hydraulics, you're pushing a liquid, and a liquid basically behaves like a solid in the fact that you can't squeeze it to make it any smaller. Unlike air, you can compress air. Hydraulics, we see them all over the place. These are hydraulic actuators right here in these arms that stabilize this fire truck. These are also hydraulic actuators right here which raise and lower the ladder. There's probably a hydraulic actuator that will turn that ladder to pivot and point in different directions. There's the one, yep, there they are. Close-ups on them. Some of the things about hydraulics, they use a liquid and you can't compress them. They're slower. They're more precise in general because they move slower. They lubricate themselves naturally because that hydraulic fluid is a lubricant. They're not as clean because of the hydraulic fluid when it leaks. It can operate between 500 and 5,000, so you can huge pressures inside of hydraulic lines. I mean, 5,000 pounds on every square inch of a line, that's a lot. They can produce more power. So you'll see hydraulics used in applications where you need to lift a lot of weight. Now, some of the first hydraulic water wheels, grinding grain into its constituents, hydroelectric dams, aqueducts, the turbine propeller. Hydrostatic. Maybe you've heard of your lawnmower being a hydrostatic drive. It's actually using hydraulic fluid to turn the wheel. The motor is not directly turning the wheel. Hydraulic fluid is turning the wheel. Pascal. Pressure. Pressure is equal to force divided by area. So you can push down on the big one, push down on the small one, and you get like so this is kind of like mechanical advantage in the fact that you have a large volume here, so this goes a very small distance, but then you get a big distance out. So you can use this, if you push on this one, you can get this is a mechanical advantage less than 1, so if you push on this side, you're going to get a lot of distance out. If you push on that side, then you get a little bit of distance out. So using it the other way, we get a mechanical advantage bigger than 1. Flow rate. Liquids, they have a certain amount of volume, like gallons per minute. It moves at certain velocities. That'd be like meters per second or feet per second. There are different symbols inside of an equation that we're going to use, where Q represents the flow rate, so gallons per minute, or you can convert gallons directly into cubic inches. And I think if we just Google how many cubic inches are in a gallon, and there you go, it's the first one that pops up. 231. So inside of here, there's 231 cubic inches inside of a gallon. We may have to use that. V represents the velocity, how fast it's flowing in feet per second. And then A equals area. So this is the equation that we're going to use, and I'm going to use it on a problem coming up here, where we've got a flow meter. A flow meter is attached to the main line in a hydraulic system. It measures the flow rate at 15 gallons per minute. The line has an inside diameter of 2 inches. What is the flow velocity in the meter? So let's figure this out. So we've got this Q equals V times A. So, and Q represents the flow rate, and V is the velocity, and A is the area. So right here, it says 15 gallons per minute. So that's my flow rate. So what I'm going to do is I'm going to take 15 gallons per minute. And do you remember before how I told you that 1 gallon was 231 cubic inches? So if I multiply 15 by 231, I end up getting like 3,034.65. And that's in cubic inches per minute. So my flow rate is 34.65 cubic inches every minute. The velocity. Oh, that's what it wants to know. Find the velocity. So I don't know the velocity. And then the area, it's got a diameter of 2 inches. So this area, it's a circle. It's pi times the radius, which is 1 squared. Pi times 1 squared. So if you take 34.65 and you divide by pi, basically, you would find your velocity. 1100, and that's going to be inches per minute. Inches per minute. That's how far it's going to go. So we could make that, I guess, maybe a little bit more user-friendly if you wanted to. So it's if it goes 1100 inches in 1 minute, there are 12 inches in 1 foot. So if you take 1100 divided by 12, you get like 92. So that's 92 feet per minute. So this goes about 92 feet every minute. That's how fast this stuff is going through the lines. Mechanical advantage. Mechanical advantage we talked about in our first unit, and that's the force that you're getting out divided by the force that you're putting in. So force out divided by force, like I'm a deer, or no, am I free, right? AMA, FR over FE. Force resistance divided by force exerted. Here's an example of that. So we've got 2 different size cylinders. This kind of goes back to the first little example I was using by clicking on the links here. So if I'm pushing on this one with 100 pounds, how much force is this one over here exerting, right? It asks a few questions. What's the pressure? How much force can the output cylinder lift? And then what is the mechanical advantage of the entire system? So let's give these a shot. So part A, what's the pressure? Pressure is equal to force divided by area. So the force that we're exerting 100 pounds. And the area is the area of this circle. Pi times the radius squared. And that's square inches. So if you take 100 divided by 4 pi, you end up with like 8. And that's pounds per square inch. So that's how much pressure is being exerted on every square inch inside this whole system. On every square inch, there is 8 pounds. So here you've got an area. You could figure out how much force is on this, but you figure out how many square inches that it is and multiply by 8. Part B, how much force can the output cylinder lift? We're going to use that exact same thing. Pressure is equal to force divided by area. So my pressure is 8 pounds per square inch. We're looking for the force. And now my area is this area of this circle. Pi times the radius, and the radius is 6 squared. So if I multiply 8 times 36 times pi, the force is equal to 900. That's huge. So here's a way where we put in 100 pounds and we're getting out 900 pounds. So this is a 9 times multiplier. So this is how this is how hydraulic lifts can lift a car. You know, this is how these things can pump a car like off the ground and do all of that. Like that hydraulic jack that you have to lift your car, you can do all sorts of crazy stuff with it. Part C says, what's the mechanical advantage? Am I free? The force of resistance is 900. The force that I am exerting 100. So my mechanical advantage, assuming that's 100% efficient, is 9. This has an actual mechanical advantage of 9. So that's how these things work kind of as simple machines. The Bernoulli effect. The Bernoulli effect, it says that if you've got a flow in a fluid, if you make the volume smaller, the velocity has to increase. So an increase in velocity results in a decrease in pressure. So it goes faster through this. And this is what they say a lot of times how airplanes fly. Here I'm over at Google and I just typed in Bernoulli principle GIF, and here's a cross section of a wing, and you can see as the air right here that the air is moving the same speed, like the green and the blue above it, but when it hits that wing, the wing splits it and it has to move faster over the top, which makes that a low pressure. So if you have a high pressure down below and a low pressure up above, that's what we call lift. So some people think of airplanes working on the Bernoulli effect, and that it makes a high pressure because of the slow-moving air underneath and a low pressure. So like there's no such thing as suck, but it like almost sucks it up in the air because of the high pressure down below it. Low pressure, high pressure because of the speeds. Here's a couple more examples of the Bernoulli effect at work. This is a fun one that I like to do with my leaf blower at school. You just take maybe you have a leaf blower at home, and you can totally do this. You can do it with a hairdryer and like a ping pong ball. Your ball will be totally suspended on top of that, and it won't fall off. You can even tip it to the side, because if the ball starts going off, then the air starts moving faster on that side, which creates a low pressure, and it gets sucked back in. The high pressure on the other side pushes it back to the other side. So it will stay stuck there, and you'll see it like wobbling back and forth because of the Bernoulli effect. It wants to fall, but the air on top goes faster, which creates a lower pressure, and the higher pressure pushes it back over the center. Another really fun one you can do with the Bernoulli effect: take a couple of balloons, tie them up, and you'd think that if you blew air in between the balloons, blowing the air would make them like separate. But believe it or not, blowing air through balloons actually makes them come together, because the air goes faster, which makes a low pressure, and that low pressure, the higher pressure on the outside, ends up pushing them together. The Bernoulli effect at work. Viscosity is another word for thickness. How viscous a liquid is. So maybe you've heard of like 10W30, 5W30, 14W20, like different weights of oil. It's talking about its viscosity, and that's related to what temperature is the oil going to be in? What's the operating temperature of the motor? Common hydraulic system components. Again, you've got your reservoir down at the bottom. The lines, kind of like what we had in our hydraulic one. There's a filter to filter any particulates so they don't get going into the valves and the actuators and the pumps and things like that. So here's the pump. Pump's pulling it out, pumping it around. You've got your valve right here. Oops. So your valve controls which side of the cylinder that goes into, if it extends or retracts, goes through a filter, back to a reservoir, and so on. All right, friends, that's all I've got for you today with hydraulics. Hope you learned a little bit of something. Thanks for watching.